Welcome in mechanical system design. Today we will solve the one numerical on optimum design topic. So here it is a problem statement. A thin spherical pressure vessel is subjected to an internal pressure of 4 Newton per mm square. The mass of empty vessel should not exceed 125 kg. If the factor of safety is 3, design the pressure vessel with the objective of minimizing the gas storage capacity out of the following material. So the three materials are given M1, M2 and M3, and ultimate tensile strength SUT is given for M1 material 500, M2 material 250 and M3 material 420. Then mass density is also given a rho in kg per meter cube. For M1 material it is a 7800 kg per meter cube. For M2 2800 kg per meter cube, and for M3 it is a 8400 kg per meter cube. So we will solve this problem by using optimum design method. So first step, basic configuration sketch and given parameters. So what are the given conditions that we are going to write here? So in diagram you can observe the it is a pressure vessel, spherical pressure vessel, and PI is the internal pressure acting onto the inside pressure vessel. So the PI is given as a 4 Newton per mm square. So that will be equal to 4 into 10 raised to 6 Newton per meter square. Then maximum mass limit is given 125 kg. Then factor of safety is given as a 3, and our objective is maximizing the gas storage capacity, that is nothing but volume of the vessel. Next, design parameters. In second step we discuss about the design parameters for that pressure vessel. So let V is the gas storage capacity of the spherical vessel in meter cube, that is volume. D is the diameter of the spherical pressure vessel in meter. T is the wall thickness of the vessel in meter. M is the mass of empty vessel in kg. M max is the maximum allowable mass of the empty vessel in kg. P is the mass density of, not P, it is a rho. Rho is the mass density of vessel material kg per meter cube. Pi is the internal pressure in Newton per meter square. Fs is the factor of safety. Then sigma T is the tensile stress induced in the vessel wall Newton per meter square. And SUT is the ultimate tensile strength of the vessel material Newton per meter square. So these are the design parameter for pressure vessel. So in next step we will discuss about the primary design, developing the primary design equation. So the most significant functional requirement to be maximized is the gas storage capacity of the vessel is. Therefore V is equal to pi by 6 d cube. So this is the standard formula for the pressure vessel volume. Then next one is, so this is called as equation A, primary design equation. Second one is a subsidiary design equation, that is the design equation other than the primary design equation is the subsidiary design equation. So that is nothing but for mass of the empty vessel. So the M will be equal to surface area of the vessel into thickness of the vessel into density of the vessel. So the mass of the empty vessel is equal to pi d square into T into rho. So this is the second equation B, called as a secondary or subsidiary design equation. Then also stress induced in the vessel is also called as a subsidiary or secondary design equation, which is sigma T is equal to pi di or pi d by 4 times T. So this equation C, B and C are called as a secondary or subsidiary design equations. Next one, fifth one is a limit equation, LE. So it will give the satisfactory range for the stress. So the your mass of the empty vessel will be less than or equal to the maximum mass of the pressure vessel. And second one is your circumferential stress or tangential stress or hook stress should be less than or equal to SUT upon factor of safety. So this will be your allowable value for the stress inside for the pressure vessel. So the equation D and equation E are called as a limit equation. Now we are in next step we are classifying the parameters. So the parameters, then specified limit, then limited parameter, and unspecified and unlimited parameters. So here functional requirement parameters are nothing but internal pressure and factor of safety, which are specified, and unspecified are volume. Then undesirable effect parameters are mass and stress. Then geometrical parameters are d, diameter of the vessel, and wall thickness of the vessel. And material parameters are limited, that will be density and ultimate tensile stress. So this is the classification of the parameters. Next one is combining the uh, subsidiary design equation with the primary design equation. So first combine two subsidiary design equation, that is equation B and equation C, to eliminate the unspecified and unlimited parameter T. Therefore, from equation B and C, what we get m into sigma T is equal to pi d square T rho into pi d by 4T. So here T will get minimized or neglected. So pi, so you'll get m into sigma T is equal to pi into pi into d cube into rho by 4. So after simplifying this, we will get the diameter of the pressure vessel. D cube is equal to 4m sigma T upon pi into pi into rho. So this is new developed PDE for diameter. Now combining the equation F with the primary design equation A to eliminate the unspecified and unlimited parameter D. Therefore, V is equal to pi by 6 D cube. So that will be equal to, we know D cube. So pi by 6 into 4m sigma T upon pi pi rho. So pi will get cancelled. So what we will get? We'll get the volume. V is equal to 2 by 3 m into sigma T by pi into rho. So you'll get the new equation. So equation G shows that there will be the effect of limit equation D and E in developed PDE. This is the case of normal specification. Okay. Next, combining the limit equation with the developed PDE. Therefore, from the developed PDE equation G, volume is directly proportional to the mass, and volume is directly proportional to the tensile stress of the pressure vessel. So for maximizing the volume, the parameters m and sigma T should be placed at the upper limit, that is the m max and SUT upon factor of safety. Therefore, equation G becomes V is equal to 2 by 3, m becomes m max upon pi into rho, and your sigma T will be SUT upon Fs. That is a factor of safety. Therefore, V is equal to 2 by 3 m max upon pi Fs SUT upon rho. Therefore, by simplifying this, you will get the final volume equation, that is the final primary design equation, as a 6.944 into 10 raised to minus 6 SUT upon rho. So to maximize volume or gas volume, the material selection factor SUT upon rho should be maximized. Therefore, in next selection of the material, by simply considering the material parameters, that is SUT and rho, we are calculating the material selection factor SUT upon rho. So here you will get the values of for first material, second material, and third material. That is the material selection factor for M1, M2, and M3. So the selection material is M2 with SUT upon rho. So the maximum value of the material selection parameter is considered. So M2 material get the maximum value, that is nothing but 89,285.714. So this will be less and this will be again less. So maximum material parameter should be material selection parameter SUT, ratio of SUT upon rho is selected. Then next step, determination of elimination parameter. So the elimination parameters D and T can be determined by using the subsidiary design equation. So the substituting the limited values of m and sigma T in equation B and C. So from equation B, we have a m max is equal to pi d square T into rho. So we'll get the d square T 0.01421. Then from equation C, we'll get sigma T is equal to pi d by 4T. So from here we'll get the D by T ratio as 83.33. Then putting the equation Ij, or simplifying the equation I and J, we'll get the diameter of the pressure vessel. D is equal to 1.05796. That will be our answer. Now putting the value of D in either this equation, in equation J, or in equation I, we'll get the thickness, wall thickness of the pressure vessel equal to the 0.127. Our last step is to maximize the gas pressure storage capacity. From equation H. We are having a formula V is equal to 6.944 into 10 raised to minus 6 into SUT upon rho. So 6.944 into 10 raised to minus 6 into 89,285.714. So we will get the volume maximum gas storage capacity of the pressure vessel equal to the V is equal to 0.61999. So the final value will be V is equal to 0.62 meter cube. So from equation A, B, and C, that is a primary design equation and subsidiary design equation, factor of safety is 2, and also factor of safety is 2. From primary design equation, factor of safety is 2, and from subsidiary design equation, factor of safety is also 2. So the NF is equal to the NS. This is the case of the normal specification. Means in this way, this design of the pressure vessel is called as a optimum design. So in this problem, what we have done, we have just calculating the maximum gas storage capacity of the pressure vessel for minimizing the, or for optimizing the diameter of the pressure vessel and wall thickness of the pressure vessel. And also we calculate the material parameter ratio, that is SUT upon rho. So which is plays the important role for the maximizing the gas storage capacity and minimizing the diameter and wall thickness of the material. So thank you for watching the problems on optimum design based on the Johnson's method of optimization.